Hello, my name is Kermarrec, and let me present my recently created lab, Scalable Computing System. So I'm going to start by sharing my screen with you guys. Here we go. And then start this show. Okay, so this is again the name of my lab, and let me tell you what we are interested in. So basically, artificial intelligence is all over the place, and this has been made possible over the past years, mainly for two reasons, because there is a huge volume of data available out there first, and second, there are efficient machine learning algorithms that are able actually to process them and come up with extremely good models. Now, what I want to say that beyond the machine learning algorithms and the availability of data, there is also something which is extremely important, is actually the fact that you can process this data and you can make the computation of these algorithms very efficient. And this has nothing to do with the accuracy of the machine learning algorithms, but everything to do with system support. And there are many ways you can actually improve all these algorithms by improving working out what kind of distributed systems that you have in mind for a particular application, how you should schedule and synchronize a different job, for instance, in data centers, so that everything is done as fast as possible with minimizing the communication, what kind of data structure you want to use and where you want to store your data. And all of these are actually system specs, and they are as important today to run those critical algorithms. So just let me give you a little bit of background on myself and on the topic that I've been working on over my career. So basically, my research of area is distributed systems, okay? So after my PhD in France, I moved to Microsoft Research in Cambridge, where I started to work at the very beginning of peer-to-peer systems. So we were really the pioneer in this area, and we applied this to many different applications such as streaming, file storage, and so on and so forth. Then in 2004, I came back to INRIA as a research director and worked on large-scale systems. I had a team of about 20 people, and then slowly moved from streaming application and file sharing and storage towards machine learning algorithms, and especially with a focus on recommendation systems. To the point that in 2015, I founded a company, a startup called Mediego, who is still, that I sold last autumn, but still a running company, and actually I'm still involved with them, which give me a lot of very interesting problems in practice. And basically in Mediego, what Mediego does is providing personalization services for online publishers, such as typically online newspapers. So our customers are the big players, big newspapers in France and some in Switzerland and also some in Denmark. And basically we're providing them with a way to personalize their websites as well as all the email that they are sending, newsletter that they're sending to their clients. And from January, I joined EPFL as a full professor, and I'm very excited to start a new group here in this exceptional environment. Okay, so basically just let me give you an example of the system that we are considering. So distributed systems can be, a data center, can be, peer-to-peer systems of any size, and can be composed of everything that is called of edge computing. Now, the way the big classes of algorithms and methodology that we're using mostly been using in my career are mostly gossip-based algorithms, also called epidemic algorithms, and this is extremely relevant nowadays actually. Or we are also very interested in everything related to privacy. So how you actually compute some stuff on encrypted data, such as homomorphic encryption, how you communicate the data if you want some privacy, and so on and so forth. And the way I see problems are mostly graph-based problems, right? I mean, social network is a graph, recommender system can be seen as a graph, and so on and so forth. So these are actually the tools that we're using. And now, again, I completely switch to the applications that are relevant very relevant today, which are machine learning application with a specific focus on recommenders and analytics, because this is what I was doing in my company. And again, we are addressing this both on the theoretical side and practical side. And out of the 20 PhD students that graduated under my supervision, basically you have all this range of profile. Now there are, most of them are doing research, some in academia, some are working with Google, Amazon, Facebook, and some other professors in different universities in Europe, mostly, or researchers. Okay, and I keep very good links with all of them, so that's good. Okay, so now let me just give you an example of a problem that we're currently working on. The idea is to try to optimize a given graph topology for machine learning. So graph topology, I mean the way that the nodes which are computing something together are actually connected. Now, you may have heard of federated learning. So this is an approach that Google proposed. Basically, the idea is that they came up with this because today the data is basically produced on edge devices such as mobile phone, for instance. In addition, those devices may have some computing capabilities. And finally, users are more and more reluctant to actually send the data all over. So the idea of federated learning is that you have a server orchestrating the computation, and each device, instead of having the model trained on the server, train locally the model based on its local data. Then it's sent back after the iteration it was supposed to do to the server, which aggregates all the gradients and send back the updates for the new model, and so on and so forth. Okay. Now, of course, in this area, you have different things to account for, and especially you have to account for the non-uniformity of things. And this can be both statistical in the sense that you may have, for instance, a few nodes which have, I don't know, classes of pictures. This one has only pictures of cars, this one has only pictures of dogs, and then there's a huge number which have pictures of boats, say. So you have to account for this non-uniformity in the distribution, data distribution. But not only, it can also be a non-uniformity in terms of systems. So if, for instance, if you have a very slow node, it will slow down the entire system. Or if some nodes have different capabilities, they might not want to compute as much as some other nodes. So this is something that are actually challenges of federated learning model. Now, in that area, what I'm interested in is decentralized federated learning system. Why? Because, this is basically getting rid of a server. Why? Because basically you can imagine that in the data center, you want to get rid of a server which actually orchestrates this and might be a bottleneck of the system, or you might have some devices that want to self-organize to do something, and even better Internet of Things kind of network where you don't want a server to actually orchestrate this. Now, next, the question is, how should I connect those devices or those nodes, edge nodes, so that they have a model converging efficiently and rapidly, and accounting also for all this non-uniformity that you can have both in the data distribution and devices. So let me give you a more specific example on actually data distribution. So this is a uniform distribution of class. So imagine that here each circle is a node, and carries only one class of data. This one is a blue class, okay? And then it's connected to a number of neighbors, meaning that it can communicate directly to this kind of nodes, okay? Now, so here we have the random distribution of those classes all over the place. Now here is a non-uniform distribution in the sense that all the pink ones are here, all the blue ones are here, and this is the way it is connected. So what that means is that pink node here, before he hears anything about the blue nodes, the data will have to travel quite a lot in the graph. So our goal here is to try to rewire the system with an algorithms, a graph algorithm, so that actually the topology basically is optimized for the learning process, the training process of the model. So basically what we want to do is we want to make sure that each node has a good neighborhood, meaning that has a good, one or two hops away representative of all the classes, as opposed to a bad neighborhood, which is this one where some classes are very far away. And our problem here is to come up with algorithm that will make sure that the topology here is optimized, and how to rewire this with a specific algorithm. And this is challenging because you want to have some basic graph properties, and you want all the rewiring to be done locally with the local algorithms. So this was just to give you one flavor. We do many other different things, including in the area of recommendation system, and also, privacy-aware recommenders and auditing recommenders, and I'll be happy to talk more about this with you on the one-to-one meeting. Okay, so thanks for listening. And so we are a fairly small group right now because we're only 5 people. So Madeleine is our assistant, and then we have 2 postdocs and a PhD students. And as soon as the fall, there will be 2 more people joining. So it's a very exciting time to build up a research agenda at EPFL. Thank you very much for your attention.